Hi, and welcome to this next video on differentiation. In this one we're going to be looking at something called implicit differentiation. So what we're going to do is use implicit differentiation to differentiate the y variable with respect to x, which sounds a bit weird to begin with, but we'll get to it, and then look at finding gradients and turning points and applying it in the usual way. So here we go. Let's first of all figure out what we mean by implicit and explicit definitions. Okay, so up to now we've really only dealt with curves in the form y equals. And so that might be something like that, and that's easy enough to differentiate. That one there is referred to as an explicit definition because y is defined in terms of x. And so we can differentiate, and we get that, no kind of a problem at all. However, if we take something, for example, the simplest one that you'll have seen so far would be the equation of a circle, where what we've got is an equation that includes x and y, but y is not the subject, so we've got x squared minus 6x plus y squared minus 8y equals 15. That one is an example of an implicit definition. Okay, so we've got the ones that say y equals explicit, the ones that have got x's and y's contained within them. And so what we've got is an equation there, but we could take that and we could just about manage to write that in terms of y. We could define that one explicitly, but it would involve a kind of square root function if you wrote that as y equals. So it's just about doable, but not particularly nice to have to differentiate. But we can think of any number of other functions where it's just physically not possible to write it as y equals. So we've got to be able to deal with things in this form, in this implicit form. Now, what we're going to do is we're going to still find dy dx, but what we're going to do is we're going to have to differentiate those terms containing y, which is this one here and this one here. What we're going to say we're going to differentiate y with respect to x. And any time you see it appearing WRT, that's just my shorthand for with respect to. Because we're still, this dy dx, we're doing it with respect to x, which is the variable on the bottom of that notation. Okay, so that's what's going on. So let's first of all have a think about something that's very straightforward, and you look at that thinking, yeah, you know what, if we can do that. But let's just think about it in a slightly different way. Now, we've seen processes before where you essentially do the same to both sides of an equation. So the most obvious example would be if I was doing, for example, a simultaneous equation. Let's say I had something like this, and I wanted to change the, let's say, the x coefficient. So what I might do is, I've got to times the whole equation by 5 and end up with 15x plus 10y equals 25. And we know that those two things are the same because we've done the same to all parts of that equation. And we did it by multiplying each bit by 5. Well, let's do something similar here. So what we're going to do is do the same differentiation that you've done previously to get to the same result, but think about it slightly differently. So what we're going to do is we're going to differentiate both sides of the equation with respect to x. So what happens then is I'm going to say let's differentiate the left-hand side with respect to x. So I get this thing here. I'm differentiating y with respect to x. And then I'm going to differentiate this thing here with respect to x. So I'm applying the same process to both sides of the equation. And we know that this thing here, when I differentiate y with respect to x, I just get dy dx. And so on the right hand side, differentiate x cubed with respect to x, I get 3x squared, and that's what you end up with. And you're extremely familiar with that and comfortable with that. It's just that way of thinking about what you're doing on the left hand side, what's going on with this, and that's the important bit, as we'll see in the next section. So something we already knew, that if you differentiate y with respect to x, it gives dy dx. Now, let's now think about how we might differentiate a function of y with respect to x. So I'm looking at here this one. We're going to differentiate y squared with respect to x. So what I'm going to do is we're going to take that, so we're going to differentiate y squared with respect to x, and I'm going to do it by doing differentiate y squared with respect to y, and then multiply it by dy dx. And we've got a chain rule thing going on here, because if you just have a look at what would happen is the dy would cancel there against the dy there. So hopefully you can see that this thing here is simply d over dx of y squared. So it's the same as what's on the left hand side. So what we're doing, technically speaking, is we're using y as a chaining variable, this kind of dy bit being the bits that's going to cancel out. So what happens? We're going to differentiate y squared with respect to x, so we're going to do it using this thing here. So this part here, differentiate y squared with respect to y, that's just straightforward 2y. and then multiply by dy dx. So you end up with this expression here. So differentiating y squared with respect to x gives us 2y dy dx. In general, what that means is if I'm going to differentiate a function in terms of y with respect to x, I just differentiate it as normal, which is that bit there, and then essentially just multiply it by dy dx. Now, I know that seems a little bit weird and confusing, and again, it's not a result you're ever going to have to prove. You just essentially need to know that you just do your differentiating as normal using the variable that's involved, and then just multiply it by dy dx, and you're good to go. Right, that's the theory. Let's have a look at a practical example. So what we've got there is an equation of a circle, x squared minus 6x plus y squared minus 8y equals 15, and we want the equation of the tangent. So there's our circle, and we've got two tangents, one there happening when x equals 5, and one there when x equals 5. So what we're going to need to do is do some differentiating in this, come up with the gradient, and then go through our normal coordinate geometry style approach to finding the equations of the tangents. So first things first, let's differentiate this implicitly. And so what we're going to do is just do it term by term. There we go. So we're going to differentiate the x squared with respect to x, this one with respect to x, and so on through. We differentiate each term with respect to x. I put that there so you can see what's going on, but there's absolutely no need to include this step in your working. It's just demonstrating what's happening. So let's do it term by term. This one here, first of all, that's simply going to be 2x. This one here, minus 6. Those are straightforward. Here we get into the bit where we're essentially using chain rule. We're differentiating y squared with respect to x. We saw that previously. That's going to be 2y dy dx. And this one here, if I differentiate 8y with respect to y, I'm just going to get 8, and then multiply it by dy dx. So there's that one. And what happens when I differentiate 15? When I differentiate a constant, that just becomes 0. So there we go. There's our differentiation. So we get that expression there. That's exactly the same as the line above it, but I've just written it without all the gaps, so it just looks a bit more normal. And so what we've got now is, within this, we can work out dy dx. A couple of ways of going about it. You can make that say dy dx equals, and then plug in some values. That, to me, seems like a bit of extra work because we're not being asked to actually physically express dy dx as an expression. So all I'm going to do is I'm just going to plug in my x and y values. But how I hear you say, well, we haven't got the y values. Well, let's get those now. So when x equals 5, let's go back to our original equation up here, plug 5 into there, and we'll come up with some y values. So there we go. That's what happens when you chuck x in. It turns out to be a quadratic, a nice simple one. And so we've got our 2 points. You can see there. There we go. That one there is your 5, 10. That one there is the 5 minus 2. So now we've got our points on our coordinates on our curve, and we've got our function that contains dy dx that allows us to find gradients of the curve. So we've got everything we need. So on we go. That's the information that we had from the previous slide. So let's now start off by saying at 5, 10, let's plug that into here, because you'll notice now our gradient, our dy dx, will depend on knowing the y coordinate as well. So there it is. So I've put the x value in there. There's our y value going in there. What I'm going to do now is just a bit of tidying up. So I've got 2 times 5 minus 6. So that bit there, that's just got a value of 4. And here I've got 20 lots of dy dx there. I'm taking off 8 lots of dy dx there, so I've got plus 12 dy dx, r equals 0. And it's almost like you see that dy dx essentially becomes a variable in its own right. What we're going to do now is rearrange the equation to say dy dx equals. And that's just a simple job of moving the 4 over, divide by the 12, and there you go. Our gradient at 5, 10 is minus 1/3. Now that I've got that, so let's keep going. We want the equation of the tangents. This one here. Gradients minus 1/3 at the point 5, 10. Y minus y1 equals mx minus x1. It doesn't tell us how we should be writing the gradient, so the equation, so we can just bang the numbers in, and there you go. There's our equation of the tangent. Let's do exactly the same now at 5 minus 2. So we've got exactly the same principle. Bang in the numbers, do a bit of tidying up, and then a bit of rearranging to make it say dy dx equals, and we see dy dx equals positive 1/3 this time, and so therefore the equation of our other tangent is y plus 2 equals 1/3 bracket x minus 5, and there you go, problem solved. Right, on we go. Let's go for a slightly more complicated example, and this one's more like what you might get in the exam. So it says we've got a curve which has got this equation here, and it says use implicit differentiation to find dy dx in terms of x and y. So this time we actually have to get to an expression that says dy dx equals, which is slightly different to the other one. So the other thing that we've got to deal with as well, that you're going to see, is this term here. This one is the one that's going to cause a bit more of a problem that we need to do a bit more thinking about. So here we go. Let's differentiate it term by term. First bit, not a problem. Here comes our problem term, because what we've got here is essentially 3x times by y. So to differentiate that, we've got two functions multiplying together. We're going to need to use product rule. So what I'm going to do is differentiate. I'm going to treat it as one function is 3x, one function is y, so we're going to differentiate it. So first of all, differentiate 3x, and I get 3, leave the y alone, so that's 3y. And then for the second part, leave the 3x alone, differentiate y with respect to x. We know we get dy dx, or 1 times dy dx. On we go. So that's that bit sorted. Let's deal with the y squared. We know that is 2y dy dx. Differentiate minus 6x, we get minus 6. 5y, we now know becomes 5 dy dx. Differentiate 9, it's a constant, that's 0. And then we've got the 0 on the other side, so that becomes that 0 as well. So there we go. Now, we've now got to get this saying dy dx equals, because we've told we've got to get dy dx in terms of x and y. That's what this bit's saying up here. So let's just do a bit of sorting out and tidying up. So I've taken here all the terms that don't include dy dx. And then what I'm going to do is take the terms that do include dy dx and write them in a factorized version like that. So I hope to just take a moment to see, make sure you're happy with what I've done there. Essentially I've just factorized over those terms by taking dy dx out. And then on the right hand side I've still got equals 0. Now it's a case of, let's move this bit here over to the other side, so that's going to require them all changing sign. And then the final step would be to do the divide. And so there you go, you've got dy dx equals, and it's in terms of x and y as the question was being, as you've been asked in the question. Right, there we go. First bit sorted, that's part A done. Let's bash on now into part B, and we're going to use what we had from the previous slide, this thing up here. So we need the 2 points onto where dy dx equals 0. So when dy dx equals 0, we've got that. So we need to do a bit of solving here. And the first obvious step to do would be to take that bit over to the other side. And the nice thing about that is when we move that over to the other side, it's just going to become 0, because 0 times by 3x plus 2y plus 5 is still just 0. So that makes life nice and simple. The other way of looking at that would be, well, this thing here, this expression is going to be 0 when the numerator is 0. It doesn't really matter what's on the denominator. If the numerator is 0, then the value of this fraction would be 0 as well. So that would also give us this statement here. So two ways of thinking about basically the same thing. Now, what we're going to do now is, previously we were looking for a point where if dy dx equals 0, we were hoping to get that happens when x equals, for example. But we're not going to get that from here. The best we can do for now is rearrange this to make that say y equals. So what we've got is a gradient of 0 when there's a link between the x and the y coordinates, when the y coordinate is 6 minus 2x over 3. If we had have ended up with a numerical value, for example x equals, we'd have just plugged it back into the equation to come up with the equivalent y value. So let's go back to our equation here, but instead of just plugging in a numerical value, we're just plugging in this thing here. And this is what makes this this question slightly different, and this is the kind of style of thing that you're going to be up against in the exam. So let's sub this back in, put the y equals 6 minus 2x over 3 in place of y, and you end up with that, and you go, oh my god, that's looking horrific. But there's a couple of little bits and pieces we can do in here just to tidy it up a bit. So those 3's cancel there, which just makes that slightly easier. So that's the x squared, that's that one there. X times by 6 minus 2x, that's those bits here. Let's now multiply out this bracket here, this square bracket. So you've got to do a bit of careful thinking about that, and hopefully you realise you're going to end up with that fraction there. Minus the 6x, and then we've got 5 times by 6 minus 2x all over 3 gives you this fraction there, and there's the plus 9, and oh my word. On we go, let's keep plugging away. Again, a little bit of tidying up. We've got just down, this is just coincidence, we've got a couple of terms that will cancel out there, which will make our life a little bit easier. And then what I've done in this last step, I've got x squared minus 2x, tidied up that bit here. And then this one here, I've just divided by 9, so 36 divided by 9, that's the 4. Minus 24x over 9, that's minus 8 over 3x. There's the 4 over 9x squared. Same thing here, I've got 30 divided by 3, which is 10. 10 over 3, that's that bit, and then the plus 9, I haven't done anything with that yet. And so now, a little bit more tidying up, so I've got minus x squared plus the 4 over 9x squared, that gives me that bit. And then the x terms, we've got minus 8 over 3 minus 10 over 3 becomes minus 18 over 3, which is just minus 6. That's kind of nice and simple. And then I've got the 4, the 10, and the 9. That's where the 23 is coming on. And so you can see that whole horrific thing does now break down into a quadratic, which we've just got to solve. I tidied it up a little bit because I'm old school, but you can just whack your coefficients from here in. And either way you do it, there we go. From your calculator, we end up with x equals 3 or x equals minus 69 over 5. The last step, it says find the coordinates. So we need to go back and find the y coordinates, which normally would mean taking our x coordinates and sticking them back into our original equation. But we can make our life a little bit simpler because rather than going back into here and having to deal with a quadratic in terms of y, we know that our turning points are when divided x equals 0 is when we've got this association. So it's much easier to put our x values back into here than it is into here. So there we go. We've got y equals 0 or y equals 56 over 3. And the last step for me, if I'm in an exam, says find the coordinates, write them explicitly as coordinates. There they go. There's my two solutions.